very good morning. Welcome you all to this NPTEL course on Advanced Distribution System Analysis and Operation. And we'll be talking about distribution network automation and restoration study. And the subunit will be Advanced Metering Infrastructure. And popularly, the acronym is AMI. Now, deploying an advanced metering infrastructure is a fundamental early step to grid modernization. AMI provides the framework for meeting one of the modern grid's principal characteristics, motivation and inclusion of the consumer. AMI is not a single technology, but rather an integration of many technologies that provides an intelligent connection between consumer and system operator. Now, when you talk about AMI system, what are the benefits that the consumer or a customer do have because of implementation of AMI in any distribution system? Because it can access to information for smart decision making, tools to act on those decisions, more choices that were previously unavailable, and system operator benefit by enhancing customer service quality, utility operation, and asset management efficiency using AMI data. Now, AMI, which integrates technologies such as smart meter, which has a networking, which is a home area network HAN, integrated communications, data management application, standardized software interface, which also connects the grid with consumers, loads, generations, storage resources, and the integration is a key enabler of the modern grids. Now we can clearly see how, the illustration how AMI is the first step to the overall modern grid vision, and which can, this AMI system can take care of, so customer voltage measurements, customer outage detection, remote TFTN, hourly remote meter reads, remote meter programming, load control, new rate design, price signal that can be sent to customers. All these actually will be considered as a part of AMI. Now, how does AMI support the vision of a modern grid? Now, motivation and inclusion of the consumer is enabled by AMI technologies that provide the fundamental link between the consumer and the grid. Generation and storage options distributed at consumer locations can be monitored and controlled through AMI technologies. Markets are enabled by connecting the consumer to the grid through AMI and permitting them to actively participate either as load that is directly responsive to price signals or as part of the load resources that can be bid into various types of markets. AMI smart meters equipped with power quality, monitoring capabilities enable more rapid detection, diagnosis and resolution of the very important PQ problems. AMI enables a more distributed operating model that reduces the vulnerability of the grid which may be attacked by wrong elements. And AMI provides for self-healing by helping outage management system detect and locate failures more quickly and accurately. It can also provide a kind of a distribution communication infrastructure which is actually ubiquitous, having excess capacity that can be used to accelerate the deployment of advanced distribution operation equipment and applications. AMI data also provides the granularity and timelessness of information needed to greatly improve asset management and operations. Now, we can also focus on subsystems of AMI infrastructure, and this is how the schematic diagram representation of AMI. We can have actually one here, wide area network. These are the utilities, and there are certificate authorities like regulatory commissions, and then we have actually smart meters placed, and we have n number of smart meters placed through gateway connections, and then finally smart meter to the residential devices like TV, laptops, etc. Now, when you talk about smart devices, they are the advanced functionalities. End user devices, so called smart meters, include state of art hardware and software capable of time stamped measurements and communication with remote data centers. So, this is going to be my residence. Let's say you have a smart meter. The smart meter not only measures the energy consumption pattern, but also it can communicate the information about my residence to a control center through bit of analytics, which is available within the smart meters, and which can also act as a two-way communication. Unlike automatic meter reading AMR, AMI supports bidirectional communication, allowing smart devices to send data and receive control signals. Consumer interaction devices like in home displays, ISDs, inform users of their energy consumption. Smart thermostats and other load controlling devices adjust usage based on utility pricing and user defined settings. Now, meter type and sensors, smart meters fall into three main categories. One is electrical, fluid, and thermal. Additional sensors, examples for humidity, light, temperature, can be integrated depending on applications. Now, the major core meter functions are, there are two subsystems that works under a single meter. One is actually metrology and the second is communication. So, in case of metrology, we measurement influenced by accuracy, region and security. And in case of communication, which is influenced by encryption and data requirement. Essential capabilities include accurate measurement, calibration, data display, synchronization, and power measurement. Now, quantitative measurement, the meter should be able to accurately measure the quantity of the medium using different physical principles, topologies, and methods. In case of its control and calibration, although it varies based on the type, in general, the meter should be able to compensate the small variations in the system. Uh, Regarding the communication part, it's sending stored data and receiving operational commands, as well as the ability to receive upgrades of firmwares. Means the smart meter, perhaps actually send all the information where it has been connected to a control center and also receive the instructions or commands from the control center and must be in a position to upgrade itself similar to your mobile phone with a very minimum analytic, a very minimum hardware. It can also get upgraded from time to time. Now, power measurement, which is a very important and common. So we normally believe that smart meters role is actually just measurement. In the event of primary source of energy going down, the system should be able to maintain its functionalities. Means sometimes there must be a backup power supply, even though there is no supply available. The meter must be in a position to carry out its exercises for some time. It must have a display, which is also need to be operated all the time, in operation all the time. So customers should be able to see the meter information. Since this information is the base of for billing, a display is also needed as demand management at customer end will not be possible without the customer's knowledge of the real time consumption. So whenever you just bill that this many units you have used, the customer may be very keen to see that my smart meter is working and it is also reflecting the exact consumption. When there is no consumption, the reading must be zero, and when there is consumption, actually the reading must be as per the expectations. Now, synchronization, which is a very important part, timing synchronization is critical for reliable transmission of data to central hub or other collector systems for data analysis and billing. Timing synchronization is even more critical in case of wireless communication devices. Now, communication, which is basically the bridge between the smart meter and the utility system, because let's say in the campus, the distance between the major control center to my smart meter data, because all the data actually they could either be stored in a server or maybe in a cloud, but the distance is certainly quite reasonable, and communication do play a very important role, which act as a bridge between smart meter and utility systems. Supports a variety of communication methods. So, for your understanding, broadband over power line (BPL), power line communication (PLC), fixed radio frequency, and then public network such as landline, cellular, paging, and ensures reliable and secure data transmission. Now, these are different examples of communication technologies. Now, we can use actually Bluetooth communication, WiMAX, copper or optical fiber cellular, PLC or BPL, satellite, internet, GPRS. You can use any type of communication, as different type of architecture and networks are available for realization of advanced metering infrastructure, AMI. There are various mediums and communication technologies for this purpose as well. So it is up to us to take a call what type of communication medium we have to adopt for our distribution network. Now, as the utility provider and a system for storing and analyzing the data for billing purposes is needed, it should also handle DR, consumption profile, and real time reactions to changes and emergencies in the grid. There are central role where meter data management system MDMS is the core analytical and data handling module in MI, responsible for validating, editing, estimating meter data to ensure reliable information flow. Big data management with 15 minutes data interval, AMI system generate terabytes of data. Just imagine, in a year, how many sets of data need to be stored for one smart meter. And if you have millions of smart meter, it's truly a terabyte of data, and millions of terabytes of data need to be stored, referred as big data, requiring specialized tools for management and analysis. You are able, because these devices, this technology will provide you a lot of information, but an user, as a owner of the complete AMI infrastructure, I must be in a position to conclude what I am going to do with this data. Okay, so those big data, until unless I do analyze and react accordingly, having all those data is no meaning to me. So major data sources in smart grids, that is smart meters, distribution network automation system, up to 30 samples per second per sensor, third party system, DR, storage and EVs, asset management system, that is firmware updates. Vendor variability, which is different vendors define and implement MDMS differently. Some offers actually basic data storage, others include full application suites. So, core objectives of MDMS, which mainly optimize grid operation, utility management, and consumer engagement using data analytics and data mining to support informed decision makings. Now, smart meter data availability is a very interesting area where smart meter can collect data in every minute. That depends actually how, because over a period of time people start getting the data to make it more real time, so minute to few seconds, but at least smart meter can collect data in every minute for sure. The smart meter data are accumulated from specially distributed customers. Temporal and spatial variations are common. If a 1 minute data sampling rate, the smart meter data from all the consumers are conveyed to the data management system, higher bandwidth communication system and higher data storage capability become mandatory. Now, normally 15 minutes data sampling rate is followed for smart meter data collection, because 1 minute you can just go for 15 minutes data sampling, which is also okay, but it is not necessary to be a binding. That depends on the capacity of your technology. Different data and their significances: monthly energy consumption used for billing, daily energy consumption, seasonal variations, occupancy and its behavior, hourly, half hourly, 15 minutes data, peak, valley load hours, demand response, mostly used for planning, demand management, energy management, etc., are only possible through data analytics using smart meters. Voltage data, which is very important, geographically footprints or grid edge devices, and smart meter data quality issues that leads Noises, irregular data collection, and missing data become part of your whole processes. Whatever effort you put, there could be bit of noises, irregular data collection is possible, and some of the data which we miss. So your technology must be in a position to carry out analytics, even both though with those actually missing data of your system. Now, we need to actually, before we try to come out with any conclusion, all the data, those are being received, need to be processed. So, the pre processing is one of the important part where statistically or machine learning based analysis to predict missing data or to detect bad or noisy data become an important pre processing process. Now, load profiling and clustering, where load profiling refers to the classification of load curves or consumers according to electricity consumption behavior, helps to determine the consumption pattern. Performed by using clustering algorithm like k-means, clustering attest. I can easily do a bit of actually load profiling and clustering. Means once millions of smart meters data are being accumulated in a minutes basis or 15 minutes basis, those data can certainly be useful for carrying out a clustering mechanism through which I can analyze in IIT Roorkee campus on a summer 1 p.m. how much of energy is expected for carrying out the cooling load. Now, there's another important part so called correlation analysis, that is temporal correlation. Correlation between energy and consumption of system customers for two consecutive time intervals for household between zero point 0.2 0.85, and day wise correlation where the correlation between profiles of successive days, very low values to around zero point 0.2, a special correlation which reveals patterns for one household energy use with respect to that of its neighborhood for household between zero point 0.2 to zero point 0.4. So these are the standards. So, but it's a good technology. Okay, you got the meters, you measured, you transmitted, saved in a cloud or a server, but there is a great chance that the security guaranteeing that the data is not being kind of manipulated or affected through external agencies. So there are a bit of security challenges in your metering infrastructure of any distribution system. That means it should not malfunction due to technological errors or there is intentional, malware that may disturb the complete AMI infrastructure within a distribution system, within a modern distribution system. So to maintain those security, the end user privacy is very, very important. High frequency data collection as frequent as every minute from smart meter allows consumer profiling, example occupancy patterns, appliance uses, even medical conditions. Okay, and third party misuse risk is always there, which is insurance, marketing, or government entities may misuse the data. For example, if someone come to know that my residence, which is continuously using an air conditioner 24 hours, probably the Voltas and Hitachi people will reach to me for buying a new AC which is energy efficient. Okay, the load signature LS of devices reveals their identity. Protection requires load signature modernization, hiding smoothing technologies or techniques with batteries and the storages. There are a bit of legal and ethical concern exist around unauthorized usage of personal data. I may say why someone is interested to know what time I'm sleeping and what time I'm using my devices. If I'm watching TV in the midnight at 2 a.m., I mean, why someone is very keen to know about it? Probably the signatures of each and every device being used in a house is known to the smart meter. So few people may object to the legal and ethical concerns that do exist because of smart meter usages. Now, because of which Canada introduced the privacy by design called PBD principles, which includes proactive, not reactive measures, privacy as the default, embedded privacy in system design, full life cycle protection, and user-centric control mechanisms. Now, there's one more important part, very popular. Today, we are talking about cyber security. Cyber and physical security become an important area where it's a cyber threat, the neighboring areas may impact if someone wish to destabilize the complete energy grid. So there perhaps the easiest attack could be make your smart meters non-operational, which is very easy, low-hanging fruit for any terrorist attack through cyber physical system applications. So, security focuses on four key principles aligned with ISO IEC 27000 standard. So, the confidentiality, which prevents unauthorized access to metering and customer data. Integrity ensures transmitted or stored data is not tampered with, includes defense against forced control commands. Availability maintains system functionality and data access even during failures, hardware, software, and network issues. Accountability, which maintains audit trails and timestamps to track access and changes for billing and legal purposes. Just imagine, due to some error, I have been charged with, let's say, few lakhs instead of few thousands or few hundreds. Then these are actually, kind of disasters. Now, challenges. Smart meters are often installed in unsecured locations. Some AMI networks rely on low security public network. High frequency security updates are limited by bandwidth constraints in low speed sections, example, Zigbee and PLCs. Now, very, very important. Most of the, countries, especially developing countries, do face energy theft issues, okay, challenges. So, can smart meter being used as a tool to detect power theft? So, non-technical losses from theft accounts for up to 40% of generation in developing countries. So, imagine the commercial, the distribution losses, which is expected to be 15 to 20%, but that goes as high as 40% because basically we say non-accounted, but that could have been gone through theft. Because I do not want to kind of stress upon the theft as a big challenge, though it is the case, but actually education and then application technology can certainly reduce those factors quite easily. So, common theft techniques, example, wire tampering, magnets, reverse connection, are ineffective against smart meters. So, smart meters certainly reduces the theft issues because few techniques are being used for conventional meters are no more applicable. And smart meter countermeasurements, which is log zero consumption, detect abnormal conditions, open circuit, tamper proof enclosures, earth leakage indicators, and data manipulation risk, which is during collection while stored in the meter. In transit example, man in the middle attack via black hole. Now, detection methods, AI/ML based algorithms, example SBM and NN can be used. Techniques, central observatory meters, power line impedances, harmonic generations, data loggers also help detect tampering or spoofed readings. Now, what are the standards and protocols, okay, for our AMI structure? So, overview of communication standards in AMI. So, first of all, we need for standards because this AMI infrastructure not necessarily being manufactured by a single vendor, it could be of many times. So, interoperability and standards are very, very important. Effective communication in AMI requires universal protocols to ensure interoperability among devices and system. Coordination among various stakeholders is complex, but much standardization work is already done. Now, building automation, what we do, what are the protocols we use? Zigbee, JetWeb, VSCNet, LonTalk, Modbus, CBus, XPL, XAP, X10, OBIX, etc. are your building automation mechanisms or tools. And then automatic meter reading AMR, which also uses Zigbee, Modbus, MBus, DLMS IEC 62056, IEC 61107, NSI C.12.18. Now, DLMS and COSM, the common language for AMI, are being used. So, device language message specification, which is so-called DLMS, it is an abstract communication modeling for metering devices especially. And then we have actually companion specifications for energy metering, defines, which is so-called COSM, defines object models, data identification, and messaging and transport methods for energy data exchange. So, these are the different standards and protocols of your smart meter or meter infrastructures. Now, Books of DLMS specifications. We There are different books. They call it a green book, yellow book, blue book, and white book. So green book, which is architecture and protocol definitions. Yellow book is for conformance testing, and blue book is for COSM object model and identification, and white book is for glossary of terms. Now, IEC 62056 series standardized in the DLMS. We can just have a look, which is S2056 21, 42, 46, 47, 53, 61, 62. Talks about local data exchange, physical layer services, data link layer, IPv4 transport, application layer, object identification systems, interface classes, respectively. Now, there is one more important part about the costings, because today, why the complete distribution system across a developing nation like India, we could not replace everything by a smart meter because it requires a lot of cost involved. So, what are the sources of AMI, you know, deployment cost? So, this is smart devices, which is a cost, meters and end user equipments, communication network that leads to cost, infrastructure for data transfer, then data management, systems for data collection, storage, and its analysis or analytics. So these are three different segments we have to invest for smart devices, communication networks, and data management. Now, when you talk about costing, each layer, specific hardware and software keep on changing. Software development is a one-time cost, while hardware, especially the endpoint, drives expansion cost from time to time. Early planning and contingency coordination can reduce long-term expenses. We can reduce the total cost with proper planning, and advancement in electronics and continuously reducing cost, especially for meters and communication network. The smart meter cost has reduced drastically, and you can see that the AMI cost, in a percentage wise, you can say end user equipment, network hardware, installation, management, and IT, and end user equipment certainly contributes close to 50% of the total cost, which is the device which is connected at the consumer end. So, with this, let us come to an end of today's talk. Once again, I thank you all for your patient hearing and participation in the course. Looking forward to the next lecture. Thank you.